Giuseppe Gonnella and with Federico Corberi and Lucilla also, we organized this young seminar series for the Italian Society of Statistical Physics. And I have the pleasure to introduce the first speaker of today, and she is Juliette Gambaudo. And okay, hi, ciao.
Yeah.
So Juliette has got his master's degree in Paris-Saclay in the field of the physics of complex systems. And now she's at the first year of PhD under the supervision of Mathieu Genois. And she's working on temporal networks, face-to-face interaction, and pedestrian dynamics. And I think this is related to the topic of the seminar of today, okay?
Yes.
So please, Juliette. Yeah,
Thank you. Let me share my screen. Up. Can everyone see it?
Yeah.
Okay. Okay, so thank you very much. Thank you very much for giving me the opportunity to talk here. I'm very happy to present you the work I've been doing during my PhD under the supervision of Mathieu Genois in the Centre de Physique Théorique in Marseille. In this...
Yeah, I've forgotten, sorry.
Oh, no worries. In my PhD, we've been developing some models to generate temporal networks of contact using very simple pedestrian dynamics. So to give a bit more of a framework, a broader framework, we are studying face-to-face interaction, meaning gathering of people, then we are looking at how they interact with each other. And as physicists, we would like to know if there are some universal mechanisms governing these face-to-face interactions, generating some universal behaviors. So this field of work is very strongly data-driven. There is the Social Pattern Initiative that gathered a lot of data, of face-to-face data in various contexts, being hospitals, schools, or companies, or these kind of things, where participants were asked to carry a small census, and whenever there was a contact between two people, it would be detected through this census. And here I put the example of 4 of these data collections that were collected during conferences. You can find them under this paper here. And it is a view of this data through the aggregated network, meaning each node is an individual, and there is a link between the 2 nodes if there has been a contact during the experiment. But the data is not only, these are static network, but the data is not only static, because you can be in contact with someone at some point, but not be in contact at the next at another point. And they are temporal network, and you can have a glimpse of the temporal dynamic of this network here with the activity timeline of one day of one of these conferences. This one. The activity being the number of links that are active at a certain time. And you see that you have successions of high activity phases and low activity phases, the high activity phases corresponding to the coffee breaks, the poster sessions, or the lunch breaks. But so a temporal network is a branch of network science that has been studied, and there has been some observable defined on a temporal network that I will explain right now. So if you have a temporal network, you have nodes and you have links that appear and disappear, okay? And so you can look at a pair of nodes, I and j, let's say, and you can look between them the timeline of activation of the link. And this defines the contact duration, what we call the contact duration, the duration of a contact. And between 2 consecutive contacts, you can define an intercontact duration. You can also count for each pair of nodes how many times they have been in contact during the full experiment. And this is for one pair of nodes, but then taking on all the possible pairs of nodes in the network for one temporal network, you get three distribution: the contact duration distribution, the intercontact duration distribution, and the number of contact. And so these distributions in the data I described earlier, they are heterogeneously distributed. There is so these are for the four different data sets that I showed before, and there appear to be some universal mechanisms, and it has been a big question on, can we explain this? Are there some simple universal rules that would explain these universal observables? And one branch of modeling of temporal network is to try to tackle this issue is based on the hypothesis that face-to-face interaction are strongly spatially constrained, and therefore having simple model that incorporates this spatial constraint could help to reproduce this observable. And so the idea is to have a simple pedestrian dynamic. I insist on the simple. They do not need to be realistic. This is not what we want to do, but we want to have the simplest one with this spatial constraint, because there are particles evolving in a space. And we look at the generated temporal network of contact, and we see if we recover this. So before showing the actual models that we've been developing, I wanted to give a bit of overview of where this branch of model comes from. So in the physics studies of pedestrian dynamic and crowd dynamic, there have been several physics-based approach. So it started in 1995 with this paper here, which presented the model that was a gravitational model. So you had repulsive forces and attractive forces making particles evolve in a space. And with this very physics-oriented approach, they managed to recover some observed behaviors, such as if you have a corridor with two populations, one going from left to the right and one from right to the left, you see the formation of lines of that emerge from this behavior. Same here, if you have two populations that want to cross a door, you will have the formation of line as soon as one cross the door. And then it has been furtherly developed always with this physics approach of having simple heuristic. In this paper, for instance, each agent has some, depending on what the information they get from what they see, and only two heuristic wanting to optimize the movement in the space without any collision. They managed to also reproduce some very good results. And more recently, you have this group of people who do long-run dynamic in order to model pedestrian model, and then they compare to data. And so there is a rich literature on the subject. And at the same time, in the network science community, as I said, there was this, when they, with the data of face-to-face interaction, there were many attempts at modeling this heterogeneity in the distributions. And what happened was in 2013, these people, Starnini, Baunkeli, and Pastos Torres, who used the method from this community to answer the questions from this one, which was pretty cool. And in the model, what they do, to describe it quickly, is that you have a box with particle, and particle are random walking. Some can be active, some can be inactive. And you define a contact between two particles when they are close within a certain radius d. And why I call this model the attractiveness-driven model is that the specificity of this model is that each agent has a intrinsic attractiveness, making and then the probability to move depends on this attractiveness. So if saying that a particle will be more likely to move the lower the attractiveness of the neighbor is. Okay, so and so this model was opened the way to this kind of model using pedestrian dynamic to generate temporal network. It has been developed furtherly, studying some opinion dynamic or some higher order interaction, meaning interactions within groups. And in our case, what is different or what is the same is that we also have particles evolving in a space, but the main difference is that we do not consider heterogeneous particle, meaning we do not have this idea of attractiveness. All particles are equal and are considered following the same rules. And then some technical differences we wanted to, that I will not go through in this presentation, but we wanted to also check the spatial constraints, the impact of the spatial constraint by trying different shapes of the box and this kind of thing. So, okay, so this is the base of our model, and now I can describe you the actual models that we did, meaning what dynamic did we implement on these particles in order to reproduce the 3 distribution that I described earlier. So let me start with the intercontact duration distribution, meaning intercontact was the duration between 2 consecutive contacts. And so in this case, we did this work with Razia Matsumi and my supervisor, Mathieu Genois, where we simulated the most simple models that we know from statistical physics, the 2-dimensional random walk in a continuous space and a discrete time. We also tried with active Brownian particle to add some sort of short memory effect, since the new range, the new direction of a particle will be in a certain range compared to the previous direction. And then we also tried a model with a layer of complexity due to interactions between particles using the Vicsek model that is more known for bird flocks or fish schools. Where basically you have agents evolving and they align their direction with their neighbors in a certain radius. And so, as you can see, these are very simple models. They are not realistic. We do not aim at mimicking crowd dynamics. This is not the point, but we want to start from the most simple and add some bricks in order to see what it brings changes. And so you can find more details in this preprint here. And I will focus on what we see on the 2-dimensional random walk, since it's the simplest. And with the 2-dimensional random walk, what we see here, I put back the intercontact duration that we found in the data. And here is the one that we get from the 2-dimensional random walk. And we see that we recover, we managed to mimic what we see in the data. So what does it mean? It means 2 things. The first one is that it's a very good news, because if you are aiming at modeling some temporal network of face-to-face interaction that would need to be realistic concerning that would need to generate this intercontact duration, you do not need to have any to put any hypothesis on what is generating this. You just need some underlying random underlying mechanisms, because this distribution, this shape of the distribution, we recover it with a 2-dimensional random walk, but also with Vicsek, active Brownian particle, and any type of model that has this very basis of random walk. The second thing is that the slope that we see in this simulation, we can link it to the one of the first passage time of 1-dimensional random walk. Okay. To the one of the 1-dimensional random walk in a certain limit through a semi-analytical argument, which would help understanding where this distribution comes from in the data. But so, the 2-dimensional random walk is enough to generate the intercontact duration. But now let's talk about the 2 others, and I will start with the contact duration distribution. In this case, if you have a 2-dimensional random walk, I will show you now why the 2-dimensional random walk is not enough to generate a heterogeneous distribution for the contact duration. So if you have a random walking particle, they will meet another particle randomly. And the only thing that would make the contact last longer would be to meet them again randomly at the next time steps. But this is not very highly probable, and most likely they will separate quickly, and we have this very short contact distribution, the dashed line being the slope that we are aiming at. So what we understand is that we need, the challenge here is to generate longer contact. And so what comes naturally is to do a reinforcement process. So this is what we do. So we have a random walking particle and they can meet, and we say that with a certain probability pconv, they can stop the movement and keep interacting. They will stay in this state depending on another probability p out, the probability to leave the conversation state. And once they do, they, in order not to re-enter in this loop of conversation, they drift towards a random position that they choose. So here, what is important to understand, the key information is that we add a reinforcement process depending on two parameters, the probability to enter the conversation state and the probability to leave it out. And we can explore a bit the impact of these two parameters. So here I put, so this is the model, and here I put again the distribution from the data. This is the space of parameters, and we will see for each parameters what are the results. So first of all, if we take a medium value for the probability to leave the conversation, whatever the value of the probability to enter it, the contact will be too short because the particle drifts and separates too soon. So we need something smaller. But if we take something smaller and a medium value for the probability to leave the conversation, we see that we see an overrepresentation of very longer contact, meaning that you have an overrepresentation of particles re-entering the loop and being stuck into it. And so what we see is that particles mimic best what we see in the data when both of these probabilities are very low, meaning that particles are diffusing freely most of the time without stopping to interact with people, with another particle. But when they do, they exploit this interaction a lot by staying a very long time due to this small probability p out. So this reminds us of the exploration-exploitation balance. Okay. Yes. So this was for the number, the contact duration. We managed to understand a bit what could generate it, and so this was makes us happy. And so then we wanted to tackle the number of contacts. So number of contacts is how many, to remind you what I said before, the number of contacts is the number of time each pair of particles interacted with each other during the whole process. And so the straightforward hypothesis is to say that why I interact this amount of time with someone depends on the memory I have of them. And so we add some memory process to the particles in order to reproduce this number of contact distribution. And to do this, we use this object that was defined in this paper by Valeria Delardi et al. It's called the social bond network, and how it works is very simple. It's so you have the pedestrian simulations that generates a temporal network of contact, and from the temporal network of contact, you can construct a parallel weighted temporal network that updates itself in order to build a memory of past interactions. And the idea is simple. If I meet I and J for 1 hour, the social bond between us will be equivalent, while if I leave and they stay together for 1 hour more, the social bond between them will become stronger, like here, and the one they have with me will become weaker. And this is updating following these two rules here. And so this object allows us to keep in mind some type of memory of past interactions of our pedestrian simulations. And so once we have this, we still have random walking particle. And so we need to know how do pedestrians adapt their walk to this memory of past interaction. And so we say that you have three typical behaviors. Imagine you are in a conference break room, as we said, was the one generating the most contact. There are three types of people to you. There is people you've never met before, people you've met a bit, and people you've interacted with a lot. And we say that the three typical behaviors could be that you go towards someone you know very well, or you want to explore and meet someone new, or you are not aiming at someone, but you're just aiming at a position, like you want to take a coffee or something. And so you drift towards it. And so this is the model that we implemented. This is saying the same thing as I described earlier. What is important, the additional information that is important here is that we have, so a particle will be random walking, so just freely diffusing, and at a certain rate activate a target, meaning drifting towards a target. Target is chosen between the three choices I described before. And what is important here is that the particles do not stop targeting once they reach the target, but rather at another certain rate, s, and then to go back to purely diffusion. So here I will not go into the details of all the parameters, the impact of all the parameters, and I will focus on these two rates R and S. So here again is the distribution that we got from the data. And here I will plot different curve for each range of parameters corresponding to the full duration of the simulations, because it's a challenge to manage to keep small number of contacts with particle with larger size of the simulation. And so starting with R smaller than S, meaning particle being most of the time diffusing and less time targeting, we see that we get only short number of contacts. Then as soon as we reach R equal S, we start to get to recover some heterogeneity. And then if we have R larger than S, we even manage to recover this stability of the number of the low numbers of contact, even with very large, very longer simulations. Sorry, and so this we managed to recover the heterogeneity of the distribution. But another question is that the main parameters that were impacting was these two rates R and S. And so what I am currently working on now is that now we have explored a very complex model and tried to see what was playing which part, and now we can go back to simple and try to understand what was the key element that was generating the distributions. And so having simpler models that keep these alternations between two phases of localized and purely diffusing is the way to go, I believe. And so now I will quickly finish and conclude. So we had the three distributions that we wanted to recover and reproduce that were heterogeneous in the data, the intercontact duration, the contact duration, and the number of contacts. And we've seen that the intercontact duration distribution, you can recover it very easily. There is no need for any assumption. Then the contact duration distribution the challenge was to get some large durations of contact. So we added a reinforcement process. And the number of contact duration, the challenge was to keep the low numbers of contact with long simulations. And we tried to implement some memory of past interaction, and I am still working on trying to have the most simple and basic model to understand what is happening. And this, I thank you all for listening to me, and thank you again to the organizers, and I'm happy to answer any questions.
Okay, thank you very much, Juliette, for this very clear presentation. And maybe there are questions of someone. You mentioned active particles, but maybe I missed something because actually the audio sometimes was missing.
Okay.
Can you comment again on what is the effect of activity of persistent random motion in your result?
Okay, so yes, I didn't present this because it was not part of it, but I can show you here active Brownian particles. So in active Brownian particles, you have a particle that keep moving with by keeping some persistence in the direction because the new direction will be chosen according to a certain range. And here what we saw is that the intercontact duration is still recovered, this without any problem for any type of, any range of new parameters. Then on the other two distribution was not so clear what was relevant or not, and so was not super, didn't add anything. What we are happy with is that this is a very consistent, whatever the model we tried.
Okay. Are there other observations or questions? Yeah, let's wait. Maybe not. Okay, Okay, so we thank you again, Juliette, for the nice presentation, and we hope to meet you in the next SIFS meeting in Parma in June. And okay, so thank you again.
Thank you.
Ciao. And I think we can switch to the second speaker.